All right, welcome back. We're going to finish up section 7.3 and hence chapter 7 this time around. A couple slides, some things that are pretty self-explanatory, I think, just a little twist with standard deviation, but we're going to look at the sampling distribution of a difference between two means. So let's say we had the heights of 10-year-old girls. It can be normal. Mean is 56.4, and standard deviation is 2.7, using the subscript G to mention the girls. All right, now we got the guys here. We're going to look at those. All right, now the heights of 10-year-old boys can be modeled 55.7 inches and the standard deviation of 3.8. Okay, so we got those comparisons. So suppose we take independent simple random samples of 12 girls and 8 boys of this age and measure their heights. All right, now remember, the shape's going to be approximately normal. We got the centers of each one. We got to figure out the standard deviation of each one. Remember, we got for the girls, we got to take the actual standard deviation, divide it by the square root of our sample size of 12. Now the boys, we're only doing 8, so we got to divide by the square root of 8 there. So we've got those measures right there. Now, what can we say about the difference between the mean girls and the mean boys sample means? Okay, well, we could simulate this, of course. We get this little distribution here. And what we kind of notice is that one set of samples gives the mean of 56.09 and the boys of 54.68. If we subtract those, of course, we get 1.41 inches. All right, that's what we get right there. All right, now the mean, of course, the difference would be 0.7 inches is what we'd have there. And standard deviation then, of course, would be 1.55 inches. Now, this is the result of what we get from this is that if we choose a simple random sample from size n from population 1, the mean, standard deviation, and of course the same thing for standard population 2, the sampling distribution of the difference of means is normal. Okay, if both population distributions are normal. It's approximately normal if both sample sizes are large, bigger than 30, or if one population is normally distributed and the other sample size is large. In this case, they're both normal. So to find the difference between the means, well, take the difference between the population means. Yeah, just take the difference between those. Now, the standard deviation, again, we're going to have to take the standard deviation squared divided by the sample size of this one, girls, and then standard deviation squared divided by the sample size. Add those together, take the square root. Now again, that's as long as that 10% condition is met. Okay, we've got to be less than 10% of the population, which we are in this case, of course. And again, just keeping another little reminder or disclaimer, of course, of doing this, making sure that 10% condition is met. All right, so let's take a look at it. Fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large. According to the manufacturer, when the large setting is chosen, the amount of liquid dispensed is going to be normal with a mean of 27 and a standard deviation of 0.8. When the medium setting is chosen, the amount of liquid is supposed to be 17 ounces with a standard deviation of 0.5. Now, to test the claim, restaurant manager measures the amount of liquid in each of 20 cups filled using the large and then 25 using the medium. So let the difference be the the difference in the sample mean amount of liquid under the two settings. So what is the shape going to be? Well, we know it's going to be normal because both population distributions are normal. So it just automatically follows. All right, now let's find the mean here. Now the mean, of course, would be real easy. Just subtract the two means. 27 minus 17 is 10. That's as easy as it gets. Now standard deviation, a little more difficult. As we do the standard deviation, remember the first one was 0.8, so square it, divided by, remember we did 20 cups there. The medium had the smaller standard deviation of 0.5, so square that and divide it by, we did 25 cups of that. So what we're finding out is that standard deviation would be 0.205. So again, we don't have to check the 10% condition because we're not sampling without replacement. We are, so that's something we didn't have to do. All right, so basically what we're going to say here is that the difference between large cup and medium cup in the sample mean amounts of liquid typically vary by about 0.2 ounces from the true difference in means of 10 ounces is what we're looking at there. Okay, so there's a good little problem for us, kind of set it all together. Now, if we were to estimate the probability that the difference in sample means is within 0.25 of the true difference in means, well, yeah, we'd have to say, okay, well, our mean difference in means was 10, so let's go down from 9.25 up to 10.25. We can just use our technology in this case, so we have our lower and upper, and we had our mean of 10 and our standard deviation of 0.205. That's, sometimes using that technology is a good thing to use. We see that that probability that it's within is about 77.74%. Kind of nice to use that. Yeah, use that technology there a little bit. Okay. All right, so again, lots of different things we've done in this section. Again, hit those learning targets, pay attention to those. Again, those exercises are where we do the real learning, okay? These are kind of introductions, kind of get you comfortable with terminology, but those exercises, when you start doing the thinking and applying, I can't encourage you how important those things are. So do those exercises, look at those solutions. We provide those for you. Come see me whenever you have questions, okay? That'll wrap up Chapter 7. Until next time, I'm Mr. Boone.